Chemical reactions are all around us. It is everywhere around us and it is even within us. From the metabolism of food in our body to how the light we get from the sun is the result of chemical reactions. Chemical reactions play an integral role in the different industries, customs, and even in our daily life. They are continuously happening in our general surroundings, for example, rusting of iron, pottery, fermentation of wine, and so on. So, as organic chemistry focuses on the living organism, it is also an important matter that we get to know the different chemical reactions involved in the different organic compounds that basically happening inside our body and to the food we eat. Chemical reactions is a process that occur with two or more molecules interact to form a new product. So this is not simply a change in the physical appearance of the substance, nor simply the change in the state of compounds. This is basically a complete change of entity within. One good example of this is respiration. As we inhale oxygen from the air, it goes inside our body and this oxygen will be used in the body. As a product, it will become a carbon dioxide that will then goes out from our body since we will not use it. What happened in this conversion is what chemical reactions are. As what the equation showed, glucose, which is present in our cells. By the way, one trivia, did you know that glucose is the only carbohydrate that can go inside the cell? For example, you eat sucrose or commonly known as table sugar. Since it contains glucose and fructose as it is a disaccharide, in its structure, glucose from it goes directly in the body cells. But the fructose part has to be converted first as glucose to go inside the cell, and it is a very long process, and you will talk more about it in carbohydrate metabolism in biochemistry subject. So let's go back in the equation. Again, after we inhale oxygen that is basically from the air given by the plants, it goes a long way until it reaches our cells. Once it enters the cell, the glucose in the cells will then react and become carbon dioxide, water, and ATP, or adenosine triphosphate. This ATP here is what we use as energy in the body. This is the reason why you are standing, why you can run, so on and so forth. In this reaction, we have two important parts to consider, in which all chemical reactions has. Glucose and oxygen is what we consider as reactant. Reactant are compounds that interact to produce new compounds, while carbon dioxide, water, and ATP is the product. The product or the newly formed compounds. Some reactants has difficulty reacting with each other. That is why there's another important part in the reaction that we need to consider, and that is a catalyst. Catalysts will help in the speed up of the chemical reactions to produce a product. Some things that you need also to take note in the chemical reaction is that in the chemical reaction, a chemical change must occur which is generally observed with physical changes like precipitation, heat production, color change, so on and so forth. A reaction can take place between two atoms or ions or molecules and they form a new bond and no atom is destroyed or created but a new product is formed from the reactant. And lastly, another thing that you need to take note is that the rate of reaction depends on and is affected by the factors like pressure, temperature, and concentration of the reactant. So this is not basically one reaction is similar to the other reaction. They have different reactions with the different chemicals. There are a lot of chemical reaction that is happening in organic chemistry. However, we will narrow it down based on the reaction that could happen on organic compounds, specifically alcohol, aldehyde, carboxylic acid, ester, amine, and amide. The discussion for this will be divided with 5 subtopics. Each subtopic will focus on a specific organic compounds mentioned and also will have a 5 video discussion. So to start, let's have first the alcohol. As a review, alcohol is any class of organic compounds characterized by one or more hydroxyl groups attached to the carbon atom of an alkyl group or the hydrocarbon change that is represented as R. Did you know that alcohols may be considered as organic derivative of water? By the way, as you noticed from the previous discussion also, you always hear this word derivatives. So derivative simply means something that is based on another source. Like for example, in here, we have the water. Since the alcohol is considered as derivative of water, you can see here or you can notice here in the structure, instead of having the hydrogen from the water, which is the chemical formula of our water is H2O, or having two hydrogen and one oxygen, instead of having the hydrogen, we have the R group in the alcohol. That's why it's considered as a derivative of water. So for example, we have in the picture, as you can see here, we have the R group as 2 carbon hydrocarbon. So this is a ethyl. So this is an ethanol. Alcohols are among the most common organic compounds. They are used as sweeteners and in making perfumes are valuable intermediate in the synthesis of organic compounds or other compounds and are among the most abundant produced organic chemicals in the industry. Perhaps the two best known alcohol are ethanol and methanol or methyl alcohol. Ethanol is used in toiletry, pharmaceuticals, and fuels, and it is used to sterilize hospital instruments. It is moreover the alcohol in alcoholic beverages. So the next time you have your wine or your beer, please see in the label if you can see the ethyl alcohol. The anesthetic ether is also made from ethanol. Methanol is used as a solvent, as a raw material for the manufacture of formaldehyde and special resins and special fuels in antifreeze and for cleaning metals. Most of the common alcohols are colorless liquid at room temperature. Water and alcohols have similar properties because of water molecules contain hydroxyl group that can form hydrogen bonds with other water molecules. And with alcohol molecules, likewise, alcohol can form hydrogen bonds with other alcohol molecules as well as with water. Because alcohols form hydrogen bonds with water, they tend to be relatively soluble in water. The hydroxyl group is referred to as the hydrophilic or the water-loving group because it forms hydrogen bond with water and enhances the solubility of an alcohol in water. Alcohols with higher molecular weight tend to be less water soluble because the hydrocarbon part of the molecule, which is a hydrophobic water hating, is larger with increased molecular weight. Because they are strongly polar, alcohols are better solvents than hydrocarbons for ionic compounds and other polar substances. Alcohols may be classified as primary, secondary, or tertiary according to which carbon of the alkyl group is bonded to hydroxyl group, or it is based on which carbon atom is bonded to the hydroxyl group, which is our OH. A primary alcohol is an alcohol in which the hydroxyl-bearing carbon atom is bonded to only one carbon atom. A secondary alcohol is an alcohol in which the hydroxyl-bearing carbon atom is bonded to two other carbon atoms. A tertiary alcohol is an alcohol in which the hydroxyl-bearing carbon atom is bonded to three other carbon atoms. To simplify, as you can see in our primary alcohol, we have, or in classifying the alcohol, we only need to see where is our hydroxyl group is bonded to. For example, we have here that the carbon in where our OH or hydroxyl group is bonded to will have only one R group or one carbon. Therefore, we consider that one as a primary. So, one carbon only, one primary. Next is, if our OH will have two R group that is bonded together, we consider that one as secondary. 2R group, secondary. And then, if it's tertiary, obviously, that is 3R groups. It is important in the chemical reaction that you know the classification of alcohol, as each classification will result in different products also. Let's have a practice first before we proceed to the chemical reaction of alcohols. Here you have to identify whether the following alcohol is considered as primary, secondary, or tertiary. For the first example, again, what we need to see first in classifying your alcohol is the hydroxyl group. Where is your hydroxyl group is attached to? As you can see, your hydroxyl group is attached to this carbon atom, and then you also need to see if this carbon has another attachments. So, as you can see here that since your carbon only have one R group, this is now considered as primary. Let's now have another example. So, in our example, we see first the hydroxyl group. Where is your hydroxyl group is bonded into? As you can see, our hydroxyl group are bonded to this carbon atom. And then this carbon atom, how many R groups are bonded into this specific carbon? So we can see here that this is our first R group and then another R group. Since it has two R group, therefore this is considered as secondary. Next example we have is our hydroxyl group is bonded to this carbon atom. Next is how many R groups are attached to this carbon atom. So we have first R group, second R group, and then another R group. Therefore, it has 3 R group attaching to that specific hydroxyl carbon bearing atom. Therefore, this is tertiary. Another example we have here, our OH is attached to this specific carbon atom. So this is our hydroxyl carbon atom bearing, and then it has a carbon here. So this is our first R group, and then another one is our second R group. Therefore, this is considered as secondary. Similar also with here. So since the carbon atom which our hydroxyl is attached into has R group here and then another R group here. Therefore, this is considered as secondary. Before we go to the products in which alcohol produces, let's first know how alcohols are synthesized based on the different compounds. First is through hydration process. Hydration means that it is a chemical reaction in which substance combined with water. Hydration from the word hydro or water. So here, one of the reactant is water. In the synthesis of alcohol, aside from the water, we needed one compound which is the alkene or the double-bonded hydrocarbon. Hydration is actually an addition reaction because we are adding water molecule to the alkene making alcohol as a product, and it requires acid as its catalyst. What happened in here is that this double-bonded part of alkene will be break down because of our catalyst, which is an acid. And then this water molecule will now combine to this structure. That's why it's called addition reaction, because the water molecule will be added to the structure of the alkene. So, as you can see here, our double bond is break, making only one bond. And then our water will also be break down. The hydroxyl part will come or will be bonded to the first single band of your carbon, and then the other hydrogen will be bonded to the other single band of our compound. As a product, they will now have a alcohol compound. Let's have some exercise here. So, predict the products formed by the hydration of the following alkenes. For example, for our first example, we have the 2-hexene. Since our hexene is constituting to 6 carbon atom, let's draw first the 6 carbon. So we have here a 6 carbon. So we have here 6 carbon. And then, since this is hexene or double banded, and then the position or the locant of our double bond is at its carbon number 2. So this is carbon number 1, carbon number 2. So therefore, the double bond is located here. So this is our hexene. To complete this as a 4-banded, since our carbon is a 4-banded atom, let's imagine these lines having the hydrogen. Let's just write the hydrogen na lang. So we have here the hydrogen. Again, since hydration needs a water as its reactant, so in this reaction we need another reactant, which is the water. And then again, hydration as a catalyst for us to have the reaction, we need acid. To be specific, let's have one example of an acid. Let's have the sulfuric acid. So sulfuric acid. So what happened in here is that again, the double bond will be break down, and then allowing the water molecule here to be added to our compounds. Let's just copy first the 6 carbon atom. So again, what happened here? It will be break down into single bands. Next is our hydroxyl group will be bonded or will be added to our compounds. So we have here the OH, and then this hydrogen here in the from the water will be bonded in here. Therefore, to complete our equation, we have here the hydrogen atoms. As a product, we now have a alcohol product. To be specific, our product is 2-hexanol. Let's have another example, 2-methyl-3-hexene. So to draw this structure, we still have the 6 carbon. So let's draw first the 6 carbon here. We have now the 6 carbon, and then since this is a hexene or double band, our double band therefore is at carbon number 3. So here we have first carbon, second carbon, carbon number 3. Therefore, our double band is here, and then our substituent is at carbon number 2, so here. To complete this structure, let's just have the hydrogen. Always remember that your carbon should have 4 bonds. Have here the hydrogen. Next, for us to have a hydration reaction, we need to have water. And then, we need to have acid. To be specific, let's have our sulfuric acid. So in here again, we will just, the double bond will just be breakdown. So let's draw first the 6 carbon atom. So from here, we have the constituent methyl here, and then the double bonds will break down into single bond, allowing your hydroxyl group to be bonded here, and then our hydrogen here. Therefore, this is now our product. So as our product, we now have a alcohol, or to be specific, that is 2-methyl-3-hexanol. Aside from hydration, alcohol can also be produced through the hydrogenation, or simply a chemical reaction that adds up hydrogen to molecule. It is different from the previous reaction as it adds up only hydrogen, while the previous one is adding up water. From the word itself, hydrogenation or hydrogen. If hydration is adding reaction because it adds up water to the compound alkene, in hydrogenation it is a reduction reaction, as it reduces oxygen while it gains hydrogen. This reaction happens in the compounds aldehyde and ketone. From this reaction, we need a catalyst, which is a nickel, palladium, or platinum, or in other reactions, especially to higher number of hydrocarbons, we need to use heat as our catalyst. As we can see in the reaction, the double bond of carbonyl was destroyed, allowing the hydrogen to be connected in the structure. One hydrogen will be bonded to the single bond that was previously bonded with oxygen, while the other hydrogen will be bonded to the oxygen. Let's have an example here as a aldehyde. So this is our carbonyl group. What happened in here is that the double bonds of our carbonyl will be broken down into a single bond, allowing the hydrogen atom to be bonded to our hydrogen. So it is considered as a reduction as it lost oxygen and while gaining hydrogen. So as a product for our aldehyde, we have the primary alcohol. If for example that is a ketone, still we have this carbonyl group in here, and then again the double bonds will be break down into single bond, as you can see here in the structure, and then the hydrogen, one hydrogen will be bonded to the oxygen, and then the other hydrogen will be bonded to the other single bond of the atom. Since our ketone can be found at the center atom or at the center of our structure, we can have the secondary alcohol because it has two R groups. Let's now have some exercise. Predict the product formed by hydrogenation of the following aldehyde or ketone. So for example, we have a propanol. Propanol is an aldehyde as it has this ending nal. So propanol, so 3 carbon. So let's draw 3 carbon first here. 3 carbon. And since this is an aldehyde, we can have the double bonded or the carbonyl group at the first or at the last. So let's just have it here. So to complete, let's just have our hydrogen. Again, since this is hydrogenation, we need another reactant, which is a hydrogen. And a catalyst. For example, let's have a nickel. So we have here, again, the double bond in here will be broken down, allowing one hydrogen to be bonded to the oxygen and another hydrogen to be bonded to the other single bonded structure. So we have here OH, H in here, H, and then the other hydrogen can be found in here. Therefore, we now have as a product 1 propanol. Let's have another example. We have here propanone. So since this is a 1, so there's a ketone. So let's just draw first the propanone. So since this is a ketone, we know that the carbonyl is at the center. We cannot have it at the first or at the last because that is considered as aldehyde. So to complete this structure, let's just have the hydrogen first to have a 4 bonds or 4 atom bonded to carbon. And then we have another reactant that is important in dehydrogenation, which is our hydrogen. And then to have a catalyst, let's just have the nickel. So as a result, we now have here, we can have again, the double bond will be break down into single band, and then our one hydrogen will be bonded to our oxygen, and then the other one will be bonded to the hydrogen. Therefore, we have as a product 2 propanol. And since this is 2 propanol, we have a secondary alcohol as it has 2 R group bonded to the carbon-bearing hydroxyl atom. From the synthesis of alcohol, let's proceed to the alcohol reactions, in which from the alcohol we make another compounds. Actually, these reactions is a sort of reverse from synthesis of the alcohol. Later on, you will notice this one. First is the dehydration. So if on the synthesis we have the hydration, the reverse process of it is the dehydration. From the word itself, de means removal and hydro means water. So this reaction simply is the removal of water, or the water compound is lost. The catalyst that we need are heat and either sulfuric acid or phosphoric acid. So in this equation, the hydroxyl group of alcohol will react to the other hydrogen, allowing the double bond to form a alkene and water. Sounds familiar, right? It's more or less similar to hydrogenation, only that the process is reversed. So in here, since we are subtracting hydroxyl group in the equation, this reaction is an example of elimination reaction. That is a reaction in which a molecule loses atoms or ions from its structure, or a reaction in which 2 groups or 2 atoms on neighboring carbon atoms are removed from a molecule, leaving a multiple band between the carbon atom, in this case the OH and H. But this reaction can be a mixture of reaction. This means that there would be 2 possible products that can be produced. To better analyze this, let's have an example in here. So we have the 2-butanol. In the 2-butanol, they could possibly have 2 products. So let's just have first its catalyst. So we have a acid. So we can have a sulfuric acid perhaps, and then some heat. Let's have the triangle as a symbol of heat. And then in the dehydration, there are 2 possible answers. 2-butene, which is our major product, because as you can see in here, this OH and H will be eliminated in the structure, allowing a double bond. As you can see here, we now have a double bond. And then another product or another possible product is 1-butene, which is a minor product. So as you can see here, we have the double bond at the first carbon. Notice in this equation that the major product is more highly substituted alkene. As you can see, if we are to eliminate the hydrogen and also the hydroxyl making us a water, these two compound will be highly substituted or would have a possible double bond at the center, right? So that's why we consider this one as a major product. However, since there's also a possibility, since our hydroxyl group are in here, there should be a possibility that the double bond instead of here will be in here as shown in our minor product. In 1875, the Russian chemist Alexander Zaitsev developed a rule to describe such reaction. This possible two-product reaction in here. Zaitsev rule states that in an elimination reaction, the alkene with the greatest number of alkyl group on the double-bonded carbons is the more highly substituted alkene. And thus, we have to consider that one as a product of the reaction. Another example we have here is a 3-methyl-2-butanol that will have two possible products. Let's just again write the acid, which is, let's have for example, a sulfuric acid. Do not forget to include always the catalyst. So, the two possible reaction or product in here is 2-methyl-2-butene and 3-methyl-1-butene. Since in the second example, it is more substituted alkyl group compared with the other one as shown in here. So therefore, this is our major product, this is our minor product. Did you know that dehydration of alcohol to form carbon-carbon double bond occur in several metabolic pathways in living system, such as the citric acid and also the beta oxidation pathway, in which you can further understand this one when you reach the biochemistry subject. Instead of having catalyst as an acid, we have the enzymes, and instead of an elevated heat in the laboratory, we have our body temperature, which is 37 degrees Celsius. Another chemical reaction that alcohol could yield is oxidation reaction. It is different in reduction, as instead of loss of oxygen, it gains oxygen while losing hydrogen, in contrast to the reduction as it gains hydrogen. Its catalyst is basic potassium permanganate and chromic acid. So in this reaction, as you can see, our primary alcohol, let's have this oxygen here as our catalyst, or indicating that this is an oxidation reaction. Since the oxidation reaction will have a loss of hydrogen, one hydrogen, such as in here, will be bonded to the other oxygen or the other OH in here, making a water, and then allowing the double bonded oxygen. So where did you get this oxygen? So this oxygen will be get in our catalyst as an oxidizing agent. But if for example we have in here a secondary alcohol, so in the secondary alcohol, we lost hydrogen to make us a water while gaining oxygen. So as you can see here, and if we have this secondary alcohol, we will have a ketone as our product plus a water. However, if for example that is a tertiary alcohol, so what will happen here is that since we don't have any possible hydrogen available to be lost, there is no reaction that could happen if that is a tertiary alcohol. So let's have an example here. For the first example, as you can see, the hydroxyl is bonded to this carbon, in which this carbon here has another R group. So this is considered as primary alcohol. Therefore, as our product, this carbonyl group will be formed, making us an aldehyde. So our product now is 2,2-dimethyl propanol and water. Another example here, we have a secondary alcohol because our carbon hydroxyl bearing is having 2 R group attaching to this carbon bearing hydroxyl. And therefore, we have propanone as our product and a water. But for example, we have a tertiary alcohol as shown here in the picture. By the way, what is the name of this alcohol here? So we have carbon number 1, 2, 3, 4, 5, 6. So this is 6. So we have hexanol. Our hydroxyl is bonded at the second carbon. So this is 2-hexanol. And then we have another methyl here. So this is 2-methyl. Hexanol. So therefore, this is 2-methyl 2-hexanol. So since our carbon bearing hydroxyl group is having 3 R group attaching to it, so therefore this is considered as tertiary alcohol. And again, in oxidation, since there is hydrogen atom that can be eliminated in this structure, we cannot have any reaction. Therefore, the possible product is no reaction or NR. As a summary for chemical reaction of alcohol, we have here an alkene, or the synthesis of alcohol could be based on alkene, in which the alkene will become a alcohol, and that is what we call hydration. While the reverse process of it is an alcohol converting to alkene, which is the dehydration. Another synthesis of alcohol could we get is from aldehyde or ketone present. So aldehyde or ketone will have the formation of alcohol, in which we call that one as hydrogenation, and the reverse process of that is oxidation.